Hello everyone, welcome to Quantum Guruji. So today in this video we are going to see in detail how to do the NRT analysis and the calculation. We'll also see how to make the input file for NRT calculation and how to do NRT calculation using Gaussian. So let's get started. So in the beginning, first we need to have a molecule and you need to optimize your molecule with whatever functional and the basis set you chose. After doing your geometry optimization, the frequency calculation, what you need to do is you need to perform an NRT calculation. Okay, for NRT calculation you need to make an input something like this. So here I am having a molecule of interest. So the molecule of interest is this one. Here you can see this is the molecule that I'll be doing for the NRT calculation here, and I will show you the the most contributing resonating structure, how to design and how to draw using the data in the output file. Okay, so this is my molecule. Okay, and the input file will looks like this something. So here I am using CAMB Philip, and this is the basis set I am using right now. Okay, so and here I am using the POP NBO7. So first of all, this NRT calculation you will be able to do only if you are having NBO7. Okay, so in NBO3, that is the default version built in the Gaussian 9 or 16, it won't work in that. You need to have NBO7 in order to use this NRT feature. So here we'll be giving a keyword pop equals NBO7 read. So why we are giving this read because at the end we are writing about the NRT calculation. Okay, and you can use this integral superfine, and it's up to you. Because I'm using this for purpose and I have to maintain the same methodology. That's the reason I'm using this. And this dispersion correction, since I'm using for my some other stuff, so if you are like beginner, you can exclude these things. And since I'll be using this because I have to maintain some standard for the publication level. Okay, so then this is your molecule name, whatever you want to put you can give, charge multiplicity and the coordinate, and at the after putting coordinate put a one empty space, and then you need to put a dollar sign and NBO NRT. There has to be one space here, NBO space NRT space dollar sign and okay, and after that you just put two empty space or one empty space, few empty space is required. This is the input file for your NRT calculations. So once you submit your calculation, it will take quite some time, but since it is a single point calculation, so it may not take huge time. Depending on the size of molecule, it will be done within a minute, or it may take roughly around within a minute, like 15 or 10 minutes it will be done. Okay, now so you will get a output file something like this. Okay, so you'll get something like this output file. Here you go down, and slowly going down you will see the calculation steps. So NBO7 has started the calculations over here. In the first there will be the NBO population analysis, and you go down you will see the summary of NBO, like natural population analysis. We don't need, like, if you are interested you can just analyze this. And this is the configuration, electronic configuration of each elements that has like in the molecule, right? So in case if you want to see the contribution of orbital, like how much the contribution, or in the case of hybridization, you can use these things. Okay, suppose here like in any cases, if you want to look for the the orbital composition and all the population of the orbital, you can look up here. But right now we are looking for the NRT analysis, so we'll directly go there. Going down over, you will see quickly down. Okay, so here it will start the second order perturbation. In the second order perturbation only, in down we will get this. So this is the donor receptor thing here. Okay, and going down you will see the NBO orbitals. Yeah, so now you can see from here the natural resonance theory analysis starting, right? Here you will see, so you are having a topomatrix for a leading resonating structure, right? So I have shown you my molecule, right? So that molecule will be having several resonating structure, and out of all those resonating structure, whatever is significant or contributing more is given here. This is the topomatrix. Here these 0, 1, 2, these are showing you the connectivity bond order. So 0 means there is no bond between them, 1 means there is a single bond, 2 means there is a double bond, like that it goes. So what it means is, here these are the atoms, and so here atom number, these are the number, or you can see the labeling in your molecule. So atom number, like atom is carbon, and that is the atom number 1. Atom number 1 is not connected with atom number 1, because yeah, that is a self atom, right? But atom number 1 is connected with atom number 2. Here you can see this is 2. So atom number 1 is connected with 2 with the single bond. So what we need to do is, we need to, okay, so this is my molecule here, right? This is the molecule that we are looking for. So there I have shown you that is the atom number 1 and atom number 2. So these are like labeling. I have done the labeling for this molecule. So how you can do this is so simple. In the Gauss view, you can open your molecule, okay, and go to the views, and here you label it. You can see this labeling, right? So after doing labeling, what we were looking for the file. Here you can see the atom number. Maybe I will do it side by side, means I'll put this and this PPT side by side, so that I can show you the. Okay, so here you can see the most like this is the most contributing resonating structure here. How I know that? Because if you see, this is the resonating structure, first one, which is contributing more, is given as 8.04, that is the contribution. So this one, this is the structure that I have drawn here. So how I came up to this structure is, these are the atomic labeling, right? Now you see atom number 1 is connected with atom number 2 with single bond. Atom number 1 is connected with atom number 2 with a single bond. So here if you see, there is a single bond here, right? Atom number 1 and atom number 2, single bond. Now similarly, atom number 1 is connected, is not connected with atom number 3. Atom number 1 and 3, they are not connected, so it's 0. So now you go here, it's 0 0, means there is no connectivity. Atom number 1 is connected to atom number 6 with double bond. So 1 and 6 double bond, so you can see 1 and 6 is double bond over here. So like that it goes, and you will be able to form this structure based on this the data here. Similarly, you can see atom number 1 is connected with atom number 12 with a single bond. Atom number 1 and 12 is this one. So here there will be a single bond. So you can see this is a single bond over here. Now similarly, there is, like, other than that, there is no bond here. Now come to the atom number 2, which is again carbon. Now atom number 2 is connected with atom number 1. Atom number 2 is connected with atom number 1 with a single bond. Fine. Now atom number 2 is connected with atom number 3 with double bond. Atom number 2 and 3 with the double bond here. It's atom number 2 and atom number 3. You can see double bond here, right? Now atom number 2 and atom number 13 with single bond. Atom number 2 and 13. So you can see 2 and 13 is single bond. Now similarly you go to the atom number 3, that is carbon again. So atom number 3 is connected with atom number 2 with double bond. 3 2 double bond, we have seen already. Now 3 8 with single bond. 3 and 8, which is a CH bond. You can see here that hydrogen I have not shown here. So that is a like CH single bond here. Fine. Like that you can go and see. I'll just go to this oxygen here. So this is atom number 16. Okay, this is atom number 16, this red color oxygen. So now if you see, this oxygen is connected to, directly connected to 14 with the double bond. Atom number 14 with double bond here, if you see. So atom number 16 is connected to 14, means there has to be double bond in this leading structure. You can see it's there, right? Again, atom number 16 is connected with atom number 16, that is given as this atomic so that is 2, means there is a double bond. Fine. Now so we have, based on this topomatrix, we have designed the we have this numbering, and we have this molecular structure, the resonating structure for the most leading resonating structure, right? Now similarly you can see there are several resonating structure possible, and these are the weightage, that is the contribution in the resonating structure. Now the structure 2, which is having 7.48% contribution, so this one. So how I came up with the structure is, now you know the labeling, right? Now here if you see, these are the data given here. So these are the bonds which is added or removed. The reference will be the leading structure. Okay, so now in the leading structure, if you see labeling, from here, now here this is the leading structure. Now whatever cases, if you see the bracket means bond is added. Suppose here if you see the C1 C6 in bracket, means that one more bond is added there. If anything is given without bracket, means the bond is, one of the bond is removed from there. Okay, and suppose single atom is given in the bracket like this as 13 here, means that element is losing the electron or carrying a positive charge, or the electron density is getting uh, a loss. So, and if there is a in without bracket element, means it is carrying a negative charge, or it has a a high electron density, like that it goes. Fine. Now if you see, so we'll go with this second structure here. So atom number 1 and atom number 2, the one of the bond is removed. So in the beginning structure, so without bracket means bond is added, and with bracket is bond is removed. Okay, so this is without bracket, means without C1 and C2. Initially if you see, this is your C1 and C2, so there is single bond, right? But here it is like without bracket, means one bond has been added here. So if you see the second structure, there is a one more bond added here. Okay, so C1 C2, one bond is added. C1 C6, earlier C1 C6 was this one, C1 C6. So there it was a double bond, but now it is given in bracket, means one of the bond is removed from there. Yes, this will be single bond here. So you can see this is single bond here. Similarly C2 C3 in bracket, means it is a single bond now. So C2 C3 is this one. Earlier it was double bond, now it will be single bond. Fine. Similarly C3 C4, earlier it was single bond, C3 C4. If you see C3 C4, this one here, it is a single bond, but now it is a double bond here, because if you see here it is in without bracket, and now the goes to C4 C5 in bracket, means now it is single bond, C4 C5 single bond. Earlier it was double. Again C5 C6 without bracket, means now it will be in double bond. C5 C6, earlier it was single bond, now it is double bond. So these are the changes. A remaining bond will be similar to your the initial leading resonating structure. Okay. Similarly, you can do for this contributing structure for 7.33. I'll quickly go for like another 5.88 here. Okay. So here you see the basic framework will be same, and only these are the bond which is added or like changed. Remaining will be same as your initial leading resonating structure. So right now we are looking for this 5.88. So this structure. Okay, this structure. So here if you see, so atom number 7 and atom number 12, the one of the bond is removed. So in initial structure atom number 7 and 12, this is your initial structure, it is double bond. Fine. Now since it is in a bracket, so one of the bond is removed from here. So you can see here one of the bond is removed from here. Fine. Now C7 and 13 without bracket, means it will be double bond. 7 and 13 here. So 7 and 13 if you see in the initial structure it is single bond, now it is double bond here because it is given in without bracket. So these are the two changes. Other than that, all of the bond will be same as your leading structure. So if you see, so these bonds are similar to that. Okay. Now you are having nitrogen without bracket, means there will be negative charge on nitrogen. Sulfur as 13 in a bracket, means there will be positive charge on sulfur. Fine. So like that you can based on this topometrics and this added and removed contribution of bonds, we can design the resonating structure. So like that you can see there are several resonating structure possible here, so the contributions are getting decreased. So generally right now here up to 5.17 I have shown here. Okay, so we can go up to whatever level you want. Generally like down may not be contributing that much. It will be simple breaking of double bond and putting the charges opposite to each other, right? So it depends like whatever is the leading resonating structure and most contributing resonating structure. So here this is the leading resonating structure, the first one, and other are also very close and they are contributing high in the resonating structure. So like that you can analyze the NRT or like based on your calculation. Okay, so if you have doubt pertaining to this NRT calculation and analysis, put in the comment section. Thank you for watching the video.